Hey stats class, this is the third lecture in our series. I'm going to share my screen and go over my fun PowerPoint. So exciting. I did post these slides in the module, so you have them for your reference as well. All right, here's lecture 3. We're going to talk about data and variables, distributions, descriptive statistics, and standard error. So data and variables go over things like your questions, your hypotheses, and predictions. We're going to talk about the different types of data and variables, as well as research questions. All right, so here's a concept for you. What's the question? Does ibuprofen reduce fevers? All right, you have 3 hypotheses. One is that ibuprofen doesn't affect fevers at all, one that it will reduce a fever, and another that it will increase a fever. How would you measure that? You would give someone ibuprofen and see what happens, right? So you measure their temperature before and after. And so the null hypothesis is that it doesn't affect fevers at all. So there would be no change. The first alternative hypothesis is that it will reduce the fever. So you should see the body temperature going down. And the third is that it would increase the fever. So you should see the body temperature going up. So that's what you talk about. The concept of your test is to take ibuprofen and check temperatures. Okay. We have different variables. So those are characteristics or traits that can differ among different objects. Data is the collection of observations from the variable that you are hoping to describe. These are just definitions. Populations is the group of all objects that you wish to describe, and then your sample is a representative subset of the object. So we have different types of data and variables. So we have discrete variables, which are qualitative characteristics that separate into whole units. So qualitative is different than quantitative, right? So qualitative is more of a color or sex, different characteristics on the object, okay? It's scales of measurement. A nominal scale is something that can be sorted into a group. So all the fruits, right? Apples, oranges, bananas, grapes, etc. All the pets, dogs, cats, goldfish, snakes, gross, horses, lizards. An ordinal scale is more of a ranking scale, okay? So you always rank the ordinal scale. So ranking is ordinary. That's kind of how I remember it. And so that's something like the military, right? Private, sergeant, lieutenant, cars, you'd rank in a scale of size or something along those lines. Different types. So what types of questions do you think each of these data can answer? So on a nominal scale, those objects can be sorted and they're equally weighted. So you can answer questions like how many or how frequent something is. A ranking scale, because they're sorted into groups that are related, it really gives you a lot of information about what's called the central tendency or the median. And so we'll talk a lot about that. You can test the hypothesis about a correlation. Do you remember what a correlation is? Between the discrete data that you collected on the ordinal scale and another phenomenon, such as like the relationship between cars and their weight class. So this is something that we do a lot in ecology. This is a heads up. We have continuous variables, which are quantitative, okay? They're subdivided and measured. So think of a ruler or a volume of fluid or an area of land. We have the scales of different measurements. So we have the interval scale, which can be subdivided. So there's no zero, right? So like date and time, there's no zero. And a ratio scale definitely has a 0. So it's pretty much anything that you can measure. Your research question is something that's really important. You have to determine that research question because you really need to know what kind of data you're going to collect. Is it nominal or discrete? What kind of stats tests are you going to do? Is it just the difference between things? Are you comparing averages? Are there different relationships? Because then you might be doing a regression or correlation. So you're predicting Y from X or X from Y, and how strong is that relationship between X and Y? So you want to really consider what the feasibility of answering your research question is. Like, can I even answer this with the data that I'm going to collect? And what kind of statistical tests am I going to use? So this is something that we're going to go over called frequency distributions. So we're going to talk about populations. And so that's a group of objects that you're describing. It's really hard to measure an entire population because there's too many, right? It's too expensive. So we do subsamples of things, right? Like these are little hermit crabs in the ocean. There's no way you could measure, count, whatever, all the hermit crabs in the whole ocean. So you're going to take a subsample. You just have to figure out how many you need to take in order to get the real good enough answer. And there are tests for that, and I will teach you how to do that. So we have a sample. It's a representative subset from your population. It has to be large enough so that you're not misrepresenting something. I think we talked a little bit about this last week, where I have a whole classroom of students and there are, say, 20 of you, okay? And I ask everybody how tall you are, and I take an average, and then I say the average student at CSUCI is whatever that average height is. Is that a good sample size? Probably not, right? Because there's only 20 of you and there's a couple thousand students on campus, so not a good sample. Does that make sense? So frequency of distribution. So this is just an example of chest sizes. So you measured the circumference of human chests, and these are the values. These are all the different measurements, and this is the frequency. So there were like 3 that had 33, 185 that had 36, 420 people had 37. Okay, and so this is the different count and variable. So when we do a distribution, it looks a little bit different like this. So this is the histogram of that distribution. So it's just a visual display, right? Instead of the numbers. Some people like charts, some people like graphs, some people like neither, but it's good to know how to do all of them. So there's a couple different kinds of normal distribution. In order to get these, you need really large sample sizes, which is pretty tough, but it is doable. So these are both, or all three of these are considered normal distributions. This was described by an old white dude named Francis Galton. There we go. Other kinds of distributions are uniform, so everything is equally represented. Then we have negative and positive skews, where you see on a negative skew, most of the data are not symmetric, and the left tail is way longer, meaning most of the data is on the right, and a positive skew is where most of the data is on the left, and the right tail is really long. Other distributions are called bimodal, so you have like 2 big humps in the middle. Okay, it's a lot of times when you're comparing 2 different populations. And then this is your standard bell curve, your normal distribution. This is something that you need to know what it is. We're going to talk about descriptive statistics now, looking at the mode, the median, and the mean. So we looked at the frequency distribution already, right? So the histogram is the visual of the frequency distribution of your population. All kinds of descriptive statistics can be done. You can find the mean, the median, the standard error, the variance, the skewness, the range, all kinds of stuff, as well as sections of that, doing a history. These are the things that you need to learn how to do. When you first get your data, it's really important to check this out, because this is what helps you decide what kind of tests to do, or what kind of tests you can do. So we're going to talk about the statistics of location, or what's called the central tendency. So it's the middle, right? The mean, the median, and the mode. Central dispersion is a little bit different. So it's the number that describes how either squished together all your data is, or spread out. So say you measured the height of a whole bunch of people in class, and out of 20 people, 17 of them were 5'5". Okay, so that would be a really squished or compact distribution. Does that make sense? So your central dispersion number will be really low. All right, so what do we even use this for? Right, here's a good example. What's the average GPA of an incoming CSUCY student? Or what's the median home price in Camarillo? You can use this for different examples. You can compare the average GPA of a bio and an econ major, or the median home prices in LA versus Ventura. That's what you use central tendencies for. So it's used a lot. It's not just because you're getting stuck taking this class. All right, parameters versus statistics. I want you to remember that parameters go with populations. So there's a mean, or mu, which is the funny U right there. It's a Greek letter. And then we're describing a sample. We're estimating a value, so it's a statistic, and that's the mean, or X with a bar, okay? We use statistics as estimators of population statistics, or the parameters of a population, all right? So population, parameter, mean, sample, statistic, mean, okay? X bar. Mu is for population, X bar is for sample statistic. I know it's a little tricky to remember. Sample bias, we talked about this last week. So you give yourself a distinct plan so that you don't accidentally create sample bias. I have some researchers working on taking surveys this summer, And their job is to take a survey from every third person that they come across, no matter what. And if that person says no, they don't take it, but they still stick to their method so that way there's no bias, right? What are some reasons you can think of that can create sample bias? The arithmetic mean, okay, that just means math, right? Is the mean or the average. So you'd sum up all the values, add them all up, and then divide it by how many there are, and that gives you the average, okay? This is really good for continuous data that it has a normal distribution. No, you do not have to do this math specifically, but you do it anyway. So this is mu, this funny little u, and then this weird e thing, this just means sum. And then x sub I is all the values, and then n is total population size, okay? Sample mean, so that's population mean. So the only difference here is x bar instead of mu. So I know this math stuff looks a little scary, maybe unless you really like math, but sometimes when I see things like this, I'm like, ugh. Okay, so total population size is big N, sample size is little n. So that make it feel a little bit less scary. Okay. Here's an example. These are these funky moths called Manduca sexta moths. I should have just put the common name in there. I hate Latin names. Anyway, I want you to figure out what is the mean life expectancy. So what's the math, right? You add all of them together and then you divide it by 9 because little n is for the sample. This is only a sample. This is not the whole population, okay? So what's the mean life expectancy? Did we just can't calculate a statistic or a parameter? Remember, statistic goes with sample mean and a parameter is the whole population. So which one did you do? And then how might any of this data be biased? All right, so the mean example is 43.4 days. That is the mean life expectancy for this poor little moth. Sad. All right, the median is the middle most value in the distribution. Okay, so it has an equal number on both sides. So sample median is when you put all the values like in order of magnitude, right? So from like 1 to 100, okay? And then you take n, which is the number of samples you have, right? Plus 1. So say you have 50 samples, so 50 plus 1, and then you divide it by 2 would be 25.5. So this value would be the median. All right, if n is an odd number, which it wasn't, the median is an observed value. If n is even, which it was, it's the midpoint between the two values on either side of it. Meaning, if you have 10 numbers, it's hard to pick what's in the middle, right? So it'll be between 5 and 6, okay? Because you have 5 on each side, but you can't take, say 5 or say 6, it has to be like 5.5. Does that make sense? Okay. This is really good for ordinal scale and continuous data with those skewed distributions. I'm going to give you a couple examples. So we have body mass index on the right, which is a biology example. You can see that there's a whole bunch of numbers in here, right? So we would look at this, it's slightly skewed for economics on the left. And so we use median instead of mean. All right. I want you to go ahead and find the median example. So n plus 1 divided by 2. You can do this with a calculator quick. So n is 9 plus 1 divided by 2. Over here, n is 10 plus 1 divided by 2. Find out that number, and you can find it in here. All right. What are the median life expectancies of these two samples? So 9 plus 1 divided by 2 is 5. So 40. So you go 1, 2, 3, 4, 5, 40. It's right in the middle. Over here, 10 plus 1 is 2, so it's 5.5. So we go in between 5 and 6, so it's 40.5. Does that make sense? So the median is the spot. It's not necessarily the number, it's the spot in the middle of all accounts, where the mean is actually the number, the average. All right, so that's how you can kind of remember. Median is like the divider, okay? A median in a road is that central concrete divider. It's the same thing in the math equation. It's the divider. It's not actually a number or a lane that you drive in. It's the divider between the numbers, okay? So that's kind of how you can remember it. Mode, we don't use a ton, but I have to teach you what it is anyway. It's the most frequent value represented by the greatest number. So basically like in this one, the z-score, there's a whole bunch of zeros. So that's the mode in the middle. We don't really have a lot of use for this in biology, but it's okay. All right, so what is the most frequent value here? What are the modes of each of these samples? So you look and see like, okay, there's a bunch of 40s, 2, 2, 2, okay, there's no 2, 3, 4, 5, 1, 2, 34 and 40 over here. Am I right? Yep. The mode is 40 on this side, and then there's a bimodal number 34 and 40 on that side. All right, so it's just finding the value. It's not that exciting. So now what I want you to do is calculate the mean, the median, and the mode of these guys right here. So the mean is the average, right? So 1 plus 2 plus 3 plus 3 plus 4 plus 5 divided by 1, 2, 3, 4, 5, 6. Same thing on this side. The median is n plus 1 divided by 2. So 1, 2, 3, 4, 5, 6. So n is 6 plus 1 is 7 divided by 2, and this one on the same side. And then mode. There's 2 3s on this side, 3 3s on this side. So that's probably the mode, right? Let's look. Yep. All right, cool. Distributions and descriptive statistics. So we know how to calculate the central numbers, right? We just figured all that out. But how do we describe the spread, the dispersion of numbers from the center? Well, that's a little bit trickier. So this is an example. We looked at 4 different islands and measured the height of trees, all right, random from 4 different islands. So these are the random height of trees across 4 islands. When we do the mean, median, and mode of each one, there isn't a mode, right? Fine, whatever, but there is a mean and a median for central tendencies. What about the dispersion? So what's the range, right? So what's the smallest and the largest value? Are the values between islands really different? And does this really capture the whole population, right? Is this a really good pattern of dispersion, or is it just a tiny sample? So we have to think about those things. So variables versus variability, don't confuse them. A variable is something that's being measured, right? Like height, sex, color, it's either discrete or continuous. Variability is the dispersion of that property. So say we're measuring height, okay? Variability means how many different heights there are in a group, okay? If all of the people in the classroom are like between 5 and 6 feet, okay? So are they closer to 5 foot or closer to 6 foot, right? What's the variability in that? Does that kind of make sense? Variance is the mean squared deviation. So here's our example. We have s squared is the sum of x sub I over x bar squared, and the number of samples minus 1. Okay, population variance. This is when you've measured the whole population. This is sigma squared. Population mean, see this is mu here instead of x bar up here, and total population size. So these are just things you kind of need to have in the back of your head. Excuse me. So deviation from the mean is what we call sample variance. So basically you're just figuring out how many numbers it is away from the middle. Okay, does that make sense? Oops. All right, when you take squared deviations from the mean, you're squaring them. Okay, we will go over that a little bit. Sample variance is the sum of squares. It's really important for later when we look at this. It's really good for describing dispersion. Variance usually doesn't work very well because the values are squared. And so we end up taking the square root of something instead. And so this is another conversation, but you just kind of need to understand what variance is. It's the mean squared deviation. Okay. And then standard deviation is the average distance from the mean. Okay. So you have the central tendency, how far away, how many values are, how far away from the center, and you find out that average. So you're taking the average of the distance away from the mean. I know that sounds a little bit weird, but that's what it is. So you can calculate the square root of a number in Excel by doing this fun little equation. You can calculate the square of a number here in Excel as well. Hopefully you all put in the analysis tool pack in Excel. It helps a lot for all kinds of fun math. Here's our example. If you wanted to calculate this by hand, which I'm not going to make you do, you can calculate sample standard deviation and variance for the first island. This is what you will get. this is something that you could do. You could do this by hand, but I will not make you, because your programs will do it for you. Standard error. All right, we're going to talk about standard error now. First, let's take a little review. What is the middle value in a distribution? What is the most frequent value in a distribution? Calculate the mean value for these data here. We use blank, either statistic or parameter, when characterizing an entire population, but blank, either statistic or parameter, when describing a sample. What is the name of a normal distribution? You don't have to draw it because we're on the computer, but what's the name of it? All right, here are your fun answers. It's a bell curve on the bottom. All right, we're going to keep looking at central tendency. So we're going to talk about dispersion now. So these are the stats of a dispersion, to give a single number that describes how squished or compact or spread out the distribution is. All right, and that standard deviation is the average deviation from the middle. Like how far is the most values from the mean? Like how far away when you get that big curve. All right. Standard deviation. Did I just have this in here? Nope. Okay. So this is what our normal distribution looks like. So what does any of this even mean, right? If for any normal distributed population, these are the percentages of observations. So marks on that big bell curve that you find. So mean plus or minus 1, standard deviation, mean plus or minus 1.04. So this is just a standard thing that you need to know. All right, parameter for populations and statistics for samples. It's just the difference between mean, which is the Greek letter mu, versus statistic, which is mean with X bar. Okay, we use these sample statistics to estimate the population or the parameters. All right. And then you need to think about how confident are you in your sample mean, your little mean, that does it really reflect the big population mean, right? Do 20 students really reflect the whole population of the school, or do we need to take a bigger sample? So then we're going to talk about accuracy versus precision. You may have seen something like this already. Accuracy is where your measurement approximates the true value, and precision is the degree to which those repeated measurements produce the same results. Okay. So precise and accurate is in the bottom right-hand corner. Precise because it's in the middle of the bullseye, and accurate because all 4 of them are in the middle of the bullseye. Does that kind of make sense? Sampling error is the error caused by measuring a sample instead of the whole population. So smaller samples have larger error. You do not want large error. You do not want large error. Okay. So you want to make the samples as big as possible. It reduces your sampling error and increases your accuracy when you're looking at population effects. Sampling error is estimating that population mean, right? Remember, so sample mean is the X bar and population mean is the little mu, okay? You need to have enough objects in here to really show it off. So you can see if you repeatedly collect samples from this population and graph it, you'll find that they are normally distributed if if they are distributed properly around the little mu. If not, it means that you don't have enough samples. Sample error, when you're estimating the population mean, so this is the central limit theorem. It says that the mean of a large number of samples drawn randomly from the population are normally distributed, and the means of the sample means is equal to the population mean. That means, oh my gosh, let's say mean 5 more times. What they're saying is if you take enough samples from the population that gives you a big enough distribution, you can actually say that what that sample size gives you, whatever that sample size tells you, that can count for the whole population. So you can say you're counting oak trees, okay, on Santa Rosa Island, and there's like 1,000 of them. Well, you can't hike around. You only have 2 days because it's the weekend. So you get 10 or 12 from each stand, and you end up with about 150 oak trees. Your dispersion looks like a nice bell curve of height. And so that means that you are okay to use just that number, the 152 trees that you measured, to say things about the entire population of over 1,000 trees on the island. Does that kind of help? Okay. Sample error, when you're estimating that population mean, the more samples you have, which is N, is the more accurate. All right, we just talked about this. Standard error of the means. So it's the standard deviation of the sample mean. So it just means it's the standard deviation of that smaller sample size. That's all that is. You have a bigger standard error if you have a really small group. The more N you have, which is the more samples, right? The more trees that you measure, the better your standard error is. So this will show you, N equals 3 on top, okay, out of 100 samples. And you can see that the big standard error is huge. That line across the X is pretty big. But if you have 100, if you have 20 samples on the bottom, see how much smaller that is? That means your standard error is much smaller, meaning that you're doing a much better job at really talking about what the population is. Standard error of the means. So in the math piece, it means that 68% certain that the population mean lies within plus or minus 1 standard error from the sample mean of X. The 68% is a pretty low confidence, meaning that we only are about 68% sure. So that's not great. Standard error of the means, we really want a 95% confidence level. So that means that you need to get a whole bunch of samples, okay? You have to have a confidence interval of 95%, meaning that your standard error is small. Do you see this? This is crazy for 3 samples. Look at how big those standard error are. You can't say that that's okay. So confidence intervals are what the interval is on either side of that mean or the middle, okay? And that's what you really need to pay attention to, because if you want to be able to say things about an entire population, you have to have enough, right? So we need to use that big confidence interval and be precise about it. So for large samples, so over 2,000, right? You need to be within that plus or minus 1.96 standard error. It's really important for smaller samples. You need a correction in calculating that 95%. So we use what's called T. So it's determined as A is 0.005 and your degrees of freedom. So degrees of freedom is the number of samples minus 1. So if you had like 10 samples minus 1, you have 9 degrees of freedom. That's what your upper and lower confidence limit is, plus standard error. All right, so I know this is like, whoa, what is all this stuff? But it's important. You just kind of need to have it in the back of your head so you can understand what it is. You will get better at this. When I first learned it, I cried and I was like, how am I ever supposed to remember all this jargon? So it's okay. Standard error bars, you've probably seen these, right? So it's the mean number of ant species from 6 different quadrats. And we have scrub and spinifex, so probably like where they were living. If we took more samples than 6, the standard error is expected, the standard deviation of those sample means. So see how big these bars are? They're like almost as big as the sample size. It means that it's not very precise, right? They didn't take enough samples. Variance of a sample, standard deviation, and standard error. Here are the mathematic equations. So what do I use? Standard deviation or standard error? People ask all the time. So when you're graphing your results, if you are describing an entire population, you use standard deviation. If you're just testing your hypothesis, you use standard error. You should probably write this down, okay? You're going to answer a couple questions now and off to the next thing.